What we're going to start out with today is the TCP protocol, Transmission Control Protocol. Just based on its name, what does it do?
It's a protocol for transporting information.
The transport layer transporting information. It's kind of like a record keeper. Transport Control Protocol controls the transmission control or transport control, controls the packets at layer 4, at the transport layer. And we're going to look at the IP information in a few minutes. But it's a pretty big deal. What it does is ensures that your information actually gets to the destination, doesn't it? Because we're going to have a process to where we have a numbering system, and I think in the last one we talked about it. When I was deployed, when I was in the Navy, we didn't have these clever things like email on ships. We had letters, you know, the old snail mail kind of thing. And when you're moving around in places, particularly places like the Persian Gulf, where sometimes the governments get a little odd, shall we say, and they won't necessarily let the mail go out through the embassy, although they're not supposed to stop that, or they won't let the mail go out. The stuff might arrive in the improper sequence that they were done. It doesn't make a whole lot of sense. Same thing happens in a network message. What if the information arrives out of sequence? Will that message make any sense when you try to interpret it at the destination?
Not unless it's numbered.
Not unless it's numbered, and TCP can not only number it, it can take these things and it can put them back into order. And it also knows if something didn't get there. And if something didn't get there, it says, hey, send that again. So that's kind of a big deal on this one. I get a little trigger happy here, huh? Go back here. Where does it fit in? We've already talked about that at the transport layer. This is, we have physical layer, data link, network, transport, and notice they just jump up to the application layer. This is kind of a mix between the 7-layer and the 4-layer, right? What we really would do would be to put these bottom 2 layers together, the physical and the data link layer, and call it the network access layer. So, and that kind of, to me, makes a whole lot more sense when we're looking at those things. So the underlying LAN or WAN technologies are down here. Ethernet. We define Ethernet, we define local area network topologies at layer 2, right? Kind of at layer 2 and layer 1. Because when we look at those things, we talk about the MAC address is and I'm jumping around, I know. Layer 2, or the MAC address is a layer 2 functionality, right? But it's on the NIC. So kind of NIC's kind of like that layer 1 thing. But it's layer 2. Is it layer 1 or a layer 2? It's a both. Because it's got all the voltages, that's where we plug the cable into, the definition of the connectors and all that. So it really kind of makes sense to put these two together. And the top 3 layers really work together, so it kind of makes sense to make them the application. But the network layer and the transport layer are, in fact, separate. At the transport layer, what we use today is TCP and UDP. Connection-oriented, the term that we use, connectionless. Connectionless is kind of like, you've probably heard in the news, in the military you have shoot and forget weapons. That means that you just put it out there and something else takes control. Infrared is one of the anti-air warfare shoot and forget weapons because these jets have this great big IR plume. So if you put an IR weapon up there, you don't have to be exact, you got to be close, and then it'll lock on to the plume. UDP, connectionless, something else at the application layer is going to take care of the did it get there, was it right sort of arrangement. TCP, Transmission Control Protocol, Transport Control Protocol, here called a lot of different things. It's going to have a fairly complex header. UDP is going to have a very uncomplex header. What goes into it? The Internet, the domain of the TCP protocol is the Internet. That's what we use this for. Also on our local area networks, we can use it if we're going to have things that we want to have conformation for. And it has port numbers. One of the things, if you look on the Network Plus objectives, is a list of port numbers that they want you to know, and it's pretty early in the objectives. And they're all covered here. They have things like SMTP, port 25, Simple Mail Transport Protocol. SMTP is what sends your email. And these are all on the objectives. You don't have to write them down from here. SMTP. HTTP, we all know that one, right? We got that one. HTTP is web server. So we go down here, hypertext transport protocol. I guess if I'm going to write, I should put a pin on here. If I'm going to mark, I should put a pin on here. Huh? Well, that works really well.
Got it.
You're going the wrong direction. There we go. Let's see if I can get a pin. So, HTTP. And we also have a secure HTTP, right? HTTPS, which isn't listed here, is port 443. HTTPS means that the transmission is encrypted before we send it. FTP, if you'll note here, has two different ports. One of them for connection, it says FTP data connection and FTP control connection. One of them is used to establish the connection, the other to actually send the data. Telnet allows us to do and it's port 23. Telnet's terminal network allows us to do a command line connection. We can telnet to a Windows machine and you'll get a command prompt connection where I think you're going to see telnet primarily as telnetting to switches and routers to manage them at the command line. IMAP port 143, which again is known here, is an email protocol. RDP remote desktop port 3389 is not here, allows us to connect to another machine and get a desktop, a GUI connection to it. SSH, DNS, and DHCP are on here. SSH is a secure shell. I lied about that. It's not on here. SSH is port 22 is a secure shell, which gives us an encrypted. What it really is kind of like an encrypted telnet. DNS is here. Port 53 is domain server. DNS is one of those odd ones that is both TCP and UDP, depending on how big the packet is. And port 67, boot P, 67 and 68, boot P would also be DHCP. Boot P is the older protocol, is the predecessor to DHCP. And DHCP, yeah, we all know it stands for Dynamic Host Configuration Protocol, is that thing that allows us to get an automatic IP address, right? If, and there's a term that they're going to use here, it's called APIPA, A-P-I-P-A, which is kind of a Microsoft thing. What if your machine is set up to get an IP address automatically and there's no DHCP server, nothing to give you an address? Microsoft machines will give you a 169.254 address. So if you're having trouble connecting and you do an IP config and it says 169.254, the answer is DHCP server is not answering you. Either you've got a problem probably at layer 1 because you're not making connectivity, could be at layer 2, or the server's not up or the server's out of addresses, something like that. But that's the APIPA addresses. And the TCP services, we've talked about duplex, the half, the full, and all of those different things. What kind of duplexing do we have in the system? So the header said it is a fairly complex header here. Source ports and destination ports. The ports, we just talked about some of the ports. Those are going to be destination ports. What the system does is assigns as the source port what is called in a lot of places what's called an ephemeral port, a temporary port, a random port. So you leave from some unknown port. And I think we've talked about that. It's kind of like phone calls. If you're going to call somebody, if we're going to call Josh, which phone do you have to use to call from?
You use any phone.
Any phone. Which phone do you get a call to? His phone. Same thing with these port numbers. Which port number do you have to call from? Doesn't matter. As long as it's not, and they won't assign a well-known port. What port do you have to call to if you're going to go to a web page?
The web pages.
The web pages port, which was? 80. HTTP. So the source port, destination port, source port, random port from our machine, ephemeral port. The destination port where we're going to has to be, unless we specify the port number, which you can in the address, has to be one of the well-known ports, something that's recognized by the system. Sequence number in bits, or 32-bit sequence number. The sequence number and the acknowledgement number. What this is the system that takes care of, and they're going to have a little example here, not a 32-bit number, but takes care of the numbering sequence and the startup process where we actually set this numbering sequence. The sequence number is the number that we're sending, what we're sending out. The acknowledgement number acknowledges receipt of up to a certain bit or certain number here, certain sequence number. And this is called predictive acknowledgement. I haven't seen it anyplace else except Cisco, but that's what they call it. And then we have reserved. The header length 4 bits. You notice that this is in not English, right? The header length is 4 bits, and then we have a reserved here, and reserved is still reserved. Then we have some control bits. The control bits tell the system how to handle these things. We've got urgent bit, acknowledgement, push, reset, a send, and a fin. Urgent is, in fact, an urgent communication. An acknowledgement is simply acknowledging receipt of information. Receipt, when we do an ACK, we will acknowledge receipt of sequence number something, sequence number 500. And these things are incremented, the sequence and the acknowledgement numbers, these things are incremented based on the amount of data that's in the packet.
So if it's over that, it'll just send 2 back.
It may break them up. We don't want that to happen. That's not really an issue anymore with the modern equipment, because the packets can be very, very large. IP is something that is famous for, and in the IP we can fragment. Fragments are really dangerous because the numbering sequence just is more fragments or last fragment, which gives a hacker the opportunity to stick their information in, because it doesn't really know how many fragments they are. It just knows where it fits in the packet. Because you can get in there, and we've looked at a little bit about Packet Tracer, how much information was in there. You can see all that stuff. You got to be pretty quick, honestly, to do those things. I'm not quick enough. There are tools that will recognize those things for you. A lot of hacker tools, and most hacker tools are going to be Linux-based. Actually, all hacker tools that work are Linux-based. Window size, checksum down here, the urgent pointer, 16 bits, options, and padding.
What is the SYN and
The SYN is just synchronization. We're going to talk about that in a minute in the three-way handshake. Synchronization is used at the startup. I'm also going to give you a website to go to that you can click on each of these things and I'll give you an explanation. That's linked out of your Moodle page. finish. When we're done with a conversation, you say, well, just like a telephone conversation. When you're done, you say goodbye, typically, right?
I just hang up.
You just hang up.
No, I'm kidding.
There is a hang up. There is a hang up. It's called a reset. The RST means that something wrong. I hung up. Goodbye. I'm not talking to you. That is the hang up flag here. Reset, a push flag. What these things do, the system does, is waits until the buffer gets full, whatever size the buffer, before it actually sends all the transmissions. What the push flag says is send it immediately. Don't wait for the buffer to fill up. Things that you need, actual real-time data, and the one that probably most significant that maybe means something is if you're a stock trader, which I'm not, and you're trading on short-term gains, you want to have the current pricing. Those would be push packets. Doesn't do you much good to have yesterday's prices if you're trying to trade today. So those kinds of things. Options and padding. The reason we have padding is so that it fits. It fits on a 32-byte boundary, that it makes it complete out here, and that's the only way that those are going to work. And a little bit of explanation down here. Urgent, the value of the urgent port of fills valve. Acknowledge the value. That's just what's there. These things are going to be zeros or ones. That's all we can have in them, right? Is a 0 or 1. So they will be set as a 0 or 1. And a 1 means that it's active. A 0 means that it's not active. I'm really good at making these things go wrong today, huh?
Give me a remote.
Up to 40 bytes of optional information, the 5 options as you go through those things. Actually, I went the wrong way, didn't I? On that one. UDP, this is a comparison of the TCP and the UDP. TCP is pretty big. Header. And this is the header information. UDP, source, destination port, total length, and a checksum. That's it. And then we append the data to it. Something else has to be responsible for what goes on in the UDP packet. So the TCP guarantees delivery, UDP doesn't. Something else has got to be in there. I'm going to skip a number of these, obviously. The checksum, the pseudo-header, the header, and the options. The data down here, the checksum, what does a checksum do? It's an error checking mechanism. This is all numbers, right? And the checksum can be like 50%, because what if it's wrong? Actually, that's a CRC, can be 50%, even or odd. But a checksum, if you have letters, not so good. Numbers are pretty easy. But if you got a message and it had a letter that was wrong, could you probably kind of guess what the word was? What if you get a series of numbers, a string of numbers? What if you got a string of numbers? I'm going to try this thing here, see if I can make it right without doing weird stuff. If we had a string of numbers, 2, 1, 2, if I added 2 plus 1 plus 2, I'm going to get 5, right? What I do with a checksum is I would put it after the sequence so that if I got a 2, 1, 2 with a checksum of 4, something wrong, isn't it? Then you would say that's a damaged packet, and you would ask for it to be resent. This checksum is a little more complex than that, but that's the way checksums work. We had to use those in messages transmitted to ships because they didn't always get there right. Flow control. we looked at the sliding window, and we'll look at it again in a minute, but the sliding window just says that we can send more than one packet at a time. We can put them together. What the systems do at startup are negotiate a window size, and when you start looking at the packet, you're going to see that there is a window size agreed to. So that's how much data it can happen. It can have. Heather was working on wireless this weekend, and it got a little slow, right? Wireless is slow anyway because it can't put those packets together. It has to acknowledge every packet until you get to the end standard, and then it can do that. It can create they don't call it a window size, but that's really what you're doing is creating a window with these things. But the sliding window, as the packets are received, it can continue across the transmission. And again, we'll look at that thing in a second. Sharon asked about that send. What's that send thing? When we want to start, I want to do it here. This is really not what this one is. This is an acknowledgement. But when we want to start a TCP conversation, when you go to a website, what you do is send it a send packet. Send says, I want to have a conversation. What the website then does is sends back what's called a send ACK. It's actually an ACK send. It acknowledges your send packet and says, hey, this, I want to synchronize, and send is synchronized. And what this really does is sets the numbering system that you're going to use for the packet, in the header information, the sequence numbers. What this is going to do is send the first sequence. So it's going to send the first sequence number. What the acknowledgement will do is increment that, acknowledge receipt of that. And what they're really saying is it's going to acknowledge receipt for the next packet. What it's saying is, hey, I got packet 1, and I'm not going to use a 32-bit header. Act 2, I got packet 1, send 2. This send simply establishes the numbering system for the server, for the receiver here. They use separate numbering systems, otherwise they get really confused. And then we send back from us an ACK that we acknowledge receipt of this send packet. And that's called the three-way handshake. That's all there is to it. The three-way handshake simply establishes the connection at layer 4. And we have some other things that take place in the session layer. But what it does is creates the numbering system so that we can get the reliable delivery of the data. Because if you didn't know where you started, how are you going to know what the packet number is? That's what you're doing here, is establishing the packet numbers. What this slide is actually showing is sequence 1001, 4,000 bytes. So what we're saying here is we have 4,000 bytes, 001, and we add the 4,000 to the 1001, and what's that going to be? What's 4 plus 1? We're not in binary now. 5. So we acknowledge receipt of, and I drew over it, we acknowledge receipt of 5001. This says window size 0, window size 1,000, whatever the window size is. This guy then, sequence number, the acknowledgement is 5001, so his next sequence number is going to be 5001. Sends 1,000 bytes of data, so we're going to do acknowledge the next one. It's called predictive acknowledgement when you do these things. So it establishes a three-way handshake. This is stuff that's beyond what we're going to do. This is another one. Sequence 1201, 200 bytes, got there. Sequence 1401, 200 bytes. Sequence 1601, 200 bytes. We're sending more data. We acknowledge receipt of 1601, which is the last one received. Once that happens, then we can continue with the conversation. The other guy can send more data. What you're typically going to have after you get the conversation established is a bunch of acts. Ack, acknowledging receipt of the data. Somebody's going to be sending, the other guy's going to be acknowledging receipt. So you're going to see a lot of those as you go through these kinds of systems. The three-way handshake. No. The three-way handshake. The three-way handshake, we talked about the send, the SYN-ACK, and the ACK. What does it do?
Just establishes a connection.
Establishes the connection. What does it do when it establishes this connection?
Okay, you're ready to send.
Okay, you're ready to send, but what does it do?
It synchronizes everything.
It synchronizes everything. What does it do? Checks for errors. What does it do?
All sorts of stuff.
All sorts of stuff, but what's the big thing that it does? How does it know what numbers to use? I do? How many conversations do you think are going on in the world? What happens in this, what does the send packet do? Synchronization, I've heard that word. What does it actually do? Sends the request. What does it send in its request?
Where is it sending it?
What does it send in its request? Information. What information?
Did it get from the sender?
It's the sender links up with the receiver, says, hey, this is how big the file is.
How big the file is. What is the first packet, the send packet? What do we do?
Hello.
Hello. What else does it do? Where does it get these numbers from?
Your file size.
Your file size. That's as its increment. Where does it get the first number from? Hopefully you won't forget it after we go around this world. Yeah, we'll take a break in a minute. But where does it get that number from, the starting number, the sequence numbers? That's what's in the send packet, isn't it? It establishes the numbering system. Synchronizes, I want to have a conversation. Here is the numbering system I'm going to start with. And when the other end comes back with the SYN-ACK, it establishes its numbering system. So, what does it do? What does this three-way handshake do? Establishes the connection and, okay, this can't be that hard. I just told you.
Establishes what numbers.
Tells you what numbers you're going to use. What are your sequence? And that, where else would it have gotten those sequence numbers? Was there any place else? More, the four-way handshake, the fin finishes, the fin is a four-way handshake. Sequence, ACK, sequence number, segment, send, or fin. We send a fin, acknowledges the fin, then we send a fin and it acknowledges that fin. So it's a four-way handshake in order to finish the conversation. Since this has a sequence number, if there is data that has a lower sequence number than the fin flag, you can receive it before the conversation actually finishes. TCP operation, you've done that, encapsulation and decapsulation of these things. Some of the different protocols, the telnet, what's going on with these things, close, no connection. Listen, and when you look at things on your machine, a lot of times you'll see that there is a port listening. What it's doing is waiting for somebody to try to make a connection there. How can you find out if somebody has done bad things to your computer? Look at the ports. Is there a port that shouldn't be open waiting for a connection? So a number of those connections are there. send, sent. I think the rest of this we're not going to look at because it's beyond what we need to do in this class. And there's, if you want to see, and this is in the website information. If you want to see kind of some of the stuff that other people ask about these things, those are there. So, what does the TCP do? If you can answer these questions, we'll take a break. Otherwise, I have to start over.
TCP
What?
manages traffic over the internet.
Manages tracking over the internet. What does the send packet do?
Synchronizes and it
Synchronizes
tells somebody that you're getting ready to.
getting ready and establishes a numbering system. What does UDP do? What was in it? It was a very simple header, wasn't it? It's connectionless. All it had was a source destination port,
Just
right?
send it.
And when we do the next one, we put IP with it, we're going to create a thing called a socket. So UDP is pretty simple. TCP, moderately complex, keeps track of everything. UDP, something else, has to keep track of what's going on. So we spent a lot of time, didn't really do a whole lot. Three-way handshake and acknowledgements, and then the four-way handshake for finishing the connections. Questions? I know you don't have any because you want to go on break, right?